Hey, friends, I'm Scott Hanselman, and it's Deep.net. We're here with Stephen Tobe. How are you, sir?
I'm doing very well. How are you?
I am just lovely today. We're starting our day talking about .net, but we're going deep. Folks love the Deep.net series. We're going to bring some new friends on soon to talk about new topics, topics that the team are currently working on. I love the comments. I don't know if you've seen some of the Deep.net comments. One of them was, wake up, babe. A new Stephen video has dropped. like it's some kind of an album, you know what I mean? Like the new mixtape from Deep.net. So we're going to need a soundtrack and an opening jingle soon. So that's cool.
That sounds great.
Yeah. I could just imagine someone like waking up their partner. Wake up. There's a new Deep.net video. Like, yeah, it's
definitely like, why are you bothering me?
Oh yeah. And then I talked to my spouse and she's like, who watches a 1 hour YouTube? And I was like, people lean back. People are like steepling their fingers and watching this on the big screen. So we're going to dig in today. You wanted to talk about parallelism, the concept. When I think parallel, I just think doing things twice, like at the same time, at the exact same time.
Yeah. Well, I thought it'd be fun because we talked about threading and tasks in a previous recording, and that was pretty, foundational, pretty low level. We were dealing with locks and interlocks and asynchrony and scheduling things. But one of the great things about task is it's an enabler. It lets you build higher level things on top of it, implementing various patterns and then providing those implementations of those patterns for others to employ. And there are a variety of classes, libraries in .NET that do so, and many more available on NuGet. And one of the ones that built into .NET is the parallel class. And then there are others. There's, channels and the data flow and whatnot. But I thought we could have some fun talking about parallel and some of the ins and outs and some of the things that people might not think about that it addresses and so on.
Yeah. One thing that I thought was interesting, I did a little research before this. I found a blog post that I wrote 14 years ago called Back to Parallel Basics. And I'm going to just read from from this. It says, this is literally the blog post. Okay. November 15th, 2010. Stephen Tobe is one of my favorite folks at Microsoft. This is not a real thing. Actually, I'll just share my screen because I'm that guy. You may not even realize. I didn't even know that this existed, but it did. Look at this. Here's my blog.
Well, I already love the intro. That's great.
You love the intro? Well, look at that. Boom. This is real. Okay. And we talk about, I said, I'm not gonna waste my keystrokes sitting here typing about parallel. I'm going to point you directly towards patterns for parallel programming from .NET Framework 4. People have been thinking about how to make this easier for a long time. And I remember the first time that you showed me Parallel.4 15 plus years ago. And I learned all about this. And then I asked Stephen, is this the best way to solve this problem? And then you gave me an email and I went and put it in a blog post with your permission. This is literally an email you sent me 15 years ago. It looks like the author was thinking this. It's okay, but you would not want to do this in a server application. So we talked about what would block, what wouldn't block, if you were doing this as a response to an ASP.NET request or not. It was really interesting. We got deep in it and we talked about as parallel and all this kind of stuff. And we talked about async. This has been a thing to crack for a while. And then this is some of the code that you wrote around, concurrent queue and things like that.
This makes me feel old.
Well, I just think it's interesting, right? And then it's like, this is all really complicated. So then the question was, do we go and do these lower level things that you suggested, or do we just go and use that, these parallel link one-liners? And it was a very great example. This may have been the beginning of Deep.net, because you're like, well, that would be fine, but here's how to drive stick shift. And It's like, you can choose to drive stick shift or you can choose not to. You can choose to do these things or not. But it just had me thinking like, wow, we've been talking about the right way to do these kinds of things for a very, very long time. But I feel like .NET's really dialed it in. The task parallel library was kind of where it all started, but I just wanted to show you that. It was kind of funny. It's been going on for a while.
Well, thanks. I appreciate it. I'm not sure I ever saw that before.
You didn't see I wrote this whole blog post about you? I even asked permission to go and some of these paragraphs are copy paste. This is literally with his permission. I want to call that out.
I'm sure I've looked at it at the time. But
now I have to find the email that proves that I was allowed to show your idea.
Well, if you don't actually have it, I grant you permission 14 years ago.
Thank you. I appreciate that. Okay. So anyway, Parallel's been on my mind for a very, very long time. And now we're here in a new format to talk about it and see what's happened in the last 15 years.
Yeah, it's been on my mind for a long time too. I mean, we introduced the task type and the parallel type that builds on top of it around the same time. They were basically part of the .NET Framework 4.0 release. And then pretty much every release since then, we've expanded on that core functionality, either small changes like adding additional overloads here or introducing whole new methods, like we've recently augmented the parallel class with some asynchronous equivalents to the synchronous equivalents that were there before, or whole new libraries like channels that layers on top of tasks. So we're constantly looking for places where, like, what is the next thing that developers are having to write a lot of code to tackle? All right, let's go and encapsulate that in libraries. And so that then they can write the next layer of code and not have to worry about that more foundational piece.
Cool.
Yeah. Sorry, go ahead.
No, I was just going to put your screen up, but please continue.
Oh, yeah. So the parallel class is interesting. We can just look. So there's just .parallel, and you can see there's a bunch of methods on it, but the intent is to kind of represent typical constructs you'd find in a C# application, a for loop, a for each loop, maybe a sequence of operations that have no dependencies between them, and then to encapsulate the logic of doing the sort of fork join scheduling of that work, forking off any number of workers, letting them each do their thing, partitioning the relevant work amongst them, and then joining with all of those operations. And the simplest one of which is just invoke. So you just, as you can see in the signature, like you give invoke any number of delegates. You wouldn't actually invoke console.writeLine in parallel, but we could say hello and world, and it will basically invoke both of these delegates in parallel, waiting for them both to return before this function returns. So if I just add on to this console.writeLine done, right, we're not going to get to this done operation until both of these things have completed. And it's fun to start with invoke because invoke is actually a really simple, like if you look at the code for this, it's actually quite simple. So we can write our own really easily. We're just going to have parallel invoke, and it's going to take a params action. See what? That's funny. It actually.
Wow. Okay.
It's trying to use
now,
parallel.
People have complained in the comments that maybe Copilot's making some assumptions, and you like it. We're not. This is not an ad for Copilot. It's just like. But why did it just do that? Like all you said was parallel invoke, and it was like, ah. Was that correct? Was that even close to correct?
I didn't read it.
Okay.
Well, I read it far enough to see that it was trying to use parallel.invoke to implement parallel invoke. So that's actually a good instinct, except when you're trying to teach what the implementation of parallel invoke looks like.
Yeah, that's fair.
So the parallel invoke is effectively just creating a task for every action. So I could implement this. I can even implement this with LINQ. I could say tasks equals from action in actions, select task.run. There's an example where I use Copilot to complete it for me. And then I could say task.wait all and just wait for these tests. That is basically parallel invoke. Right? It's a really simple thing. For each action, we're spawning a task, and then we're waiting for all of them. Interestingly, this is a pretty good approach, actually, when there's only a few actions. And that's the typical use for parallel.invoke, where you're calling it with 2 or 3 or 4 things. But if you had 100 things, the overhead associated with task.run kind of starts to add up. And so if you look at the real implementation, it's something more like this. If actions.length is less than, I don't remember the exact number, it's less than 10 maybe, do it this way. If it's more than that, well, then let's just parallel for each on those actions and, invoke the action, and then rely on parallel for each and all of its optimizations. Or it's possible we use parallel.for under the covers, but same idea. You just rely on it and all of its optimizations to ensure that this is appropriately optimized. And this, one of the nice things about this is it demonstrates that there's actually a reason to do this. Like parallel for each is not just launching a task for every individual element. It could, we could implement our own parallel for each. That was a, let's call this, let's do T, and this takes in the source, and we're going to run some action for each T. And so we could implement this as from item in source select, oops, but this is not this, and then task.wait all. Right? That would be a perfectly reasonable implementation. And then this can just, utilize our own custom parallel for each. These things do layer in this way, right? Parallel invoke.
Okay, well, so let's pause for a second because we might have lost people. Why is line 21 and line 10 different? Why are you not, what is the point of the, do line 10 if it's less than 10 actions in the length?
So at the moment, there's no benefit to this. Okay. Line 21 and line 10 are effectively identical.
Okay, but I want to make sure I wasn't missing something.
No, you're not missing anything. But we can now improve parallel for each, and we can avoid having a task per element. And in doing so, we can then make parallel for each more efficient for many items. And then implicitly, parallel invoke also becomes more efficient for many items.
Okay. So before we dig into that, I want to take a second and just level set a couple of things philosophically and tell me if this is okay. .NET as a runtime, as a concept, is hiding things from us, as all good systems do. It now hides processor instruction sets, so I can just write C#, write .NET, and I don't have to think about ARM or x64 or x86 unless I choose to. And it also is hiding that I might have 32 logical processors, or I might have 4, right? Like, we don't know how concurrent the actual underlying hardware is. And when I was starting out in C, I would have to think about, like, what's a reasonable amount of physical threads that this processor could handle when we started thinking about multi-threading capable. Remember, like, when hyper-threading came out, like, that was a thing. And when I was writing in Java, I used to have to think about green threads and actual threads. When you have something like line 8, where you're just saying less than 10, that feels very like it's a magic number. It's just like, well, I mean, is it a server? Is it a laptop? Is it a microprocessor? Is it a phone? It seems kind of arbitrary. How much is being hidden, and what's the right amount of hidden? Or is this just generic computer science where it's like, yeah, parallelism gets a little overheady at that number?
Yeah, so there are a bunch of places in the core libraries where there will be some hard-coded default. And you often see this in things like buffer sizes. Like, how big a buffer should I use for something? And we'll pick a number like 1,000 or 1,024 or 4096. And that number can have significant ramifications on performance, right? So if I'm reading from a file into a buffer, the larger the buffer, the more memory I'm consuming. But the larger the buffer, the fewer reads I might have to perform to read all the data from the file. If I'm reading in 4K chunks, then I have to, at best, I'm going to pull 4K from the file on each read, which means I have to make file length divided by 4K system calls and accesses to the disk and whatever else to get that data. If I used an 80K buffer, well, now I'm making 20x less, potentially 20x less calls, but I'm consuming way more memory. So there are various places where those kinds of defaults are built in. In many of those situations, I say default because they're overridable. So for example, you look at something like stream.copy2, and stream.copy2 it has an overload that just takes a destination stream, and it will pick a number to use for its temporary buffer to read from one stream and write to the other. It'll pick a number that it thinks that we thought based on performance analysis was a good one. So we actually pick a number that is large enough to try and minimize the number of copies, but small enough such that if the buffer ends up needing to be allocated, it stays off of the large object heap.
Okay. All right. Cool.
But then there's a copy2 overload that takes a buffer size. So if you don't like our choice, you provide your own. Right. Parallel invoke, there's no overload that allows you to specify the replacement for that number 10, which was selected based on performance measurements. In the extreme case where no work is being performed, and so we're just looking purely at the task.run overhead, approximately where is the cutoff between the benefits of using a task for each item versus the overhead of the one-time larger overhead of spinning up the parallel operation, but then the lower per element overhead of not needing a task.run for each. There's no overload of parallel invoke that allows you to tweak that 10 because the logic of the parallel invoke is so simple, because it really is just layering on top of other things. So the escape hatch here isn't use another overload that takes a number. It's just use parallel for each instead. And then there are options on parallel for and parallel for each that allow you to control things like degree of parallelism. So,
okay.
The comments you made, I thought you were taking your question in a different direction.
I might be heading in that direction because I also wanted to ask about performance cores and efficiency cores, and why do I have analysis paralysis about how, heterogeneous processor architecture.
That's where I thought you were going. And,
okay.
We do try and hide wherever possible the complexities, right? There's the actual parallel for each implementation is, I don't know the exact number of lines, but it's definitely not 2. It's more like 1,000, something like that.
I remember when it like 2 or 3, 4 tasks. That's a lot of tasks.
Yeah.
People were doing. Yeah. Now we can go.
We can see where some of that complexity comes in. We will try and hide as much of the complexity as we can, but there are still some things that we just can't hide. And we can try and paper over it, but. And we do. So I'm going to do a complicated example, but I think it's interesting, and we'll see how the library tries to hide it and can in some cases and can't in others.
Perfect. The people love a complicated example.
Okay. So let's write a benchmark.
All right.
So I'm going to write class. Actually, let me just, before I lose it, let me just comment this out. So let's write class tests. This needs to be public. And so we're going to write a benchmark.net benchmark. So we're going to say benchmark switcher from assembly. There you go. That's it. You were talking about Copilot. These are the kinds of things with Copilot that really help me. It's not writing the large code. It completes a thought for me that I was, something I was typing anyway. So I'm going to have an array of integers. And let's just say I've got, 32 integers. And I'm going to have a function that takes a reference to an integer value. And I'm just going to do a whole bunch of increments on it. So let's do 100 million increments on this.
Yeah, and if folks haven't seen this before, I always like to point out that really cool, using the underscore is just a comma. It's a thousands separator. It's ignored. It's a cool way to do your numeric literals. And
it just allows me to visually see that this is actually 100 million rather than having to count 8 zeros and actually make sure that's what I have. So I've got this increment function, and I'm going to write a little benchmark that uses parallel invoke. So let's just call this invoke. And my benchmark is going to do parallel invoke with 2 delegates. I'm going to call increment using value sub 0. And I'm going to call increment using value sub 1. So I've got this increment function is just 100 million times incrementing whatever value I pass by reference in. And I'm in parallel invoking it with the first element of values, and I'm invoking it with the second element of values. Very simple. Let's see how long it takes. I'm going to make one more tweak to my benchmark. I'm going to parameterize this to basically allow me to specify which index I'm actually going to increment for that second one. So instead of always using one, I'm going to run this benchmark twice, once with using the index 1 and once with using the index 31. Right? Pretty simple. And I'm going to add one more thing here because we don't care about the nanosecond differences and whatnot. I'm going to tell it to not take as much time and do this as a short run rather than what benchmark.net would normally do, which would be to take its time and get the right answer. All right, that's it. So let me run this. Window will pop up at some point. Here we go. So benchmark.net is asking me which tests I want to run. It says it found 2 benchmarks. It's building the application that contains all of its kind of cruft to allow it to do its thing. And now it's executing the benchmark where I was using index 1. So it's doing warm-ups. It's seeing how many iterations it needs to run in order to kind of get a good answer. It's decided that each iteration is taking 2 or 3 seconds, so it only needs to do a single operation because that's plenty of time. And now because I did a short run job, it's just going to run it 3 times to give me my answer. Now it's running it for the second index of 31. And you can see that one completed way faster. It was the exact same code, right? But the one that had index 1 took 2.8 seconds, and the one with index 31 took 442 milliseconds. And all I changed was what index I was, what I was passing in. And it doesn't even need interlock to see this. I could even do this just by doing this. And let me run it again. It's not going to be as large this time, but it will again see, we should see that with index 1, it's taking measurably more time than with index 31. So index 1 is taking about 190 milliseconds. We're not using interlock, so it's less. And index 31 was still about 30% cheaper.
Okay, and you can see my brow is furrowed as I'm trying to figure out if I'm just uninformed or why this is happening. And it's really significant why interlock. I mean, I could get why, interlock means everybody's got to get in line, but why
even there,
so
they were
much?
talking about different indices, so they weren't even talking about the same one. And here I've removed it, and there's still a big difference. So this is an example where we can't fully hide the intricacies of the hardware. You were talking about P versus E course. This isn't P versus E course. This is something called false sharing. So at the hardware level, when you read or write memory, the hardware knows that accessing memory is expensive. So it doesn't just move around individual bytes. It moves around units of bytes, multiple bytes in units it calls cache lines. And on a given machine, a cache line is typically 64 bytes. Some machines might have 128 byte cache lines. And so that is moved as a unit. And if you have 2 cores that are both trying to read from the same cache line, that cache line kind of has to bounce back and forth because it moves as a unit. Especially if I'm doing interlocked operations where the hardware basically is locking at the hardware level. Now those 2 threads basically take ownership of the cache line and don't allow anyone else to touch it while they're touching it. So the cache line has to kind of constantly move back and forth, even if I'm not touching the exact same value.
Okay.
So here, when I was using index of 1, I'm using 2 integers that are right next to each other in memory, right? They're 4 bytes apart, or 0 bytes apart. There's 0 bytes between them, 4 bytes between the start. Whereas when I was using 31, they're no longer on the same cache line.
All right, let's break this down for a second. I want to make sure that I understand. So there's 2 concepts you have brought up, and there are very likely people who are watching who have never heard these 2 terms. First one is false sharing. So false sharing, we have a multiprocessor system. It's 1 computer. You're on 1 machine here. But it's still multiprocessor. So you have distributed caches meant to be distributed coherent caches. We've got multiple processors modifying variables, but they're on that same cache line. So now we have that term cache line, and a cache line or a cache block is the smallest unit of data that gets transferred between main memory and the cache And that means, and they're what? They're a certain block. They're a fixed size.
Yeah,
probably some
different
power
hardware
of
has
2.
different sizes, but most consumer hardware like we use is 64-byte cache lights.
Okay, 64 byte. And because they're next to each other, these two processors are trying to go and increment this thing, and they got to get in line.
Yeah.
And then when you decided to go and have them be a little bit farther apart, now you have separate cache lines, separate cache blocks, and they're no longer constrained.
Yeah, exactly. So if
they have their own lane on the highway.
Right. The false sharing term, like true sharing would be, if both things were trying to access the exact same value. Like people look at that and, okay, there's contention on the same value. But this is false sharing because logically they're not using the same thing. They're using two different values.
Logically, conceptually, they are not the same value, but they just happen to be, it's like musical chairs, right? It's just like 2 butts, but 1 chair.
Yeah, and then you're spreading out on the multiple chairs. Right.
Exactly. This is the variable equivalent of man spreading. Okay.
That's when people buy multiple airline seats because they don't want to be crowded.
And if you didn't know that underlying thing, because there's nothing in the code here that could tell you that, you see only the result, which is, wow, that's a lot slower.
Exactly. And these kinds of false sharing issues are really hard to suss out because it's kind of this peanut butter that, layer of cost that's kind of smeared over your coding. You kind of don't know where it's coming from or what it is, but you just kind of gloss over it. But it just happened these things were next to each other. They were accessing from multiple threads, and all of a sudden things were slower than they could have otherwise.
And you could be doing games or a game engine, and then this would show up, and you're just like, what? The abstraction just leaked.
Yeah, exactly.
All right.
And so because of this, like there is logic. I mentioned there's 1,000 lines of code, in Parallel 4. Some of that logic is around minimizing the possible impact of this kind of work. Because if you've got your typical Parallel 4 is going to be something like, let's say I've got an array, right? And I've got a parallel.4 from 0 to values.length. And then I'm doing something with I, right? Or maybe I'm going to make it up. Maybe I'm incrementing I, right? If this was just naively divvying up, handing out the next I to whoever came to ask for it, we've just created a false sharing situation because you now have multiple threads possibly getting, I equals 1, and then another for getting I equals 2, and another getting I, and they're all partying on different elements. There's no real sharing. There's no threading bug here. They're all talking to different elements, but it's still going to run slower than it should have because of false sharing. So Parallel 4 tries to account for this with very complicated partitioning schemes where it will try and divvy up the work in such a way that the vast majority of it has 2 threads partying on indices that aren't logically close to each other. Of course, that has its own problems.
Okay, but the abstraction leaked, and you just try harder to hide it.
Yes,
that's awesome.
Yeah, and we do as much as we can, but at the end of the day, we can't make it fully go away. We just try and hide it as much.
But that's the 80-20 rule right there. Yeah. You know what I mean? You do some work and you hide 80% of it. That's pretty good. And if you really keep bumping into it, you watch Deep.net and you learn about it. So then you, in the example where you had it in line 18, where you decided to pick a different parameter, you said, I'll pick 32. That was intentional. You did that on purpose. How often would you have to work around Parallel.4 and be aware of it and architect around it?
The hope is that with Parallel 4, because we do have these better partitioning algorithms in place, that it's rarely actually, and it's an issue for us implementing Parallel 4. It's an issue for someone who's trying to implement their own Parallel 4. It should rarely be an issue for someone using Parallel 4.
Awesome.
It would only come into play if you were doing very specific sort of niche things where there was only, say, if I had 4 cores and I only had an array of 4 values and I was doing a lot of work per one and I was hammering on it, there's kind of nothing we can do to avoid that, because each thread is just going to be partying on a single value and they're all next to each other. And so the workaround for the developer would be, if they're in that situation and it's showing up as a measurable cost after they profile and measure and whatnot, workarounds are to space out the values. So you will see things in some code. If you look in the runtime, you'll see types that look kind of like this. I need a layout. So you'll see something like that. And then instead of having an array of int, I have an array of padded int. Right, so something like that. So now
you're wasting a ton of space there. You have the size of an int.
Yep. Okay. In order to space them out. And so because of that wasted space, we do this very rarely. But for example, concurrent queue has not per element, but has certain values that we need to space apart. Like there's a kind of a head pointer and a tail pointer, and we need to ensure that that head tail and that tail pointer are not next to each other. Because if they are, it significantly degrades. You have producers that are enqueuing stuff and you have consumers that are enqueuing stuff. And in general, they don't contend because they're talking to very different parts. But if the indices that they were accessing in increment were next to each other, that introduces false sharing. And so those are purposefully spaced out using a scheme like this.
Interesting. So 30 plus years ago, when I would do stuff in like C, we would make a struct, a padded struct, and then we would align, like we'd add like character array of 3 and just call it padding, and it was just garbage, and we'd put it at the end. We did it explicitly. Here on line 11, you're getting that nice attribute for free. You're not having to go and make false values. The compiler's probably doing it for you with line 11.
Yeah,
we used to align on like 4-byte boundaries, like a 32-bit integer align on a 4-byte boundary. In this case,
in general, the runtime handles those details, and by saying size 64, it's like, oh, okay, I'm going to create this. When I create sort of my knowledge of this type, I'm creating it as 64 bytes long, even though you're only going to end up using 4 of it.
That's cool. Okay, dig it. I'm with you.
So so we solve this problem, but there are certain ways that we could solve it where it would introduce yet other problems that kind of are sort of hardware, but kind of not. So, so let's try this. This is fun.
Yeah, this is good. Yeah, and don't forget to zoom in if you don't want to see, if you don't need to see it. Yeah, thank you.
Oh yeah. Okay. So, can I hide all this commenting a second? So let's say I had 80,000 elements. And I was going to do this this parallel for to basically process these things. Let me create a little function. I'm going to call this let's say do work, and it's going to take in some thing to do work on. Let me call this value. And the work that I'm going to do is just counting. No, that's not what I want to do. It's just counting up to value. Mm-hmm. And for each thing, it's going to invoke a little bit of logic. And that little bit of logic will just be value. And I'm going to attribute this to basically tell the, I want to make sure this loop doesn't go away by the optimizer. So I'm just, oops. Yeah. All right. So for each value that I'm passing, I'm looping from 0 up to that value, and I'm doing something. So this is the work that I'm going to logically do, a parallel for, from 0 to length, doing that work for each element. But I'm not going to use parallel for just because I want to show what can happen if we get the partitioning wrong. A very simple way to partition this would just be to do something like this. Actually, let me change. Let me just change this to be from and to, and I'll do from and to. So it's more like what parallel for would do. So I'm going to do parallel invoke, and let's say that I'm on a 4-core machine. So yeah, that's what I want to do. So I'm going to have, I'm basically partitioning this into 4 equally spaced things. Each worker is getting 20,000 elements of my 80,000 elements. So the first partition is from 0 to length divided by 4. The next one is from length to length divided by 2. The next one is from length divided to length, so basically chunking it up into 4 pieces.
Right. So yeah, so we're taking, just to slow it down, just to make sure, we're assuming there that there's a 4-processor machine, 0 to 20,000, 20,000 to 40,000, et cetera, et cetera, et cetera.
Exactly.
We have broken up the job, given them that work, and they're going to run off and do it. And we're presuming that when we hand them the work, they are now independent, working on their own thing, doing their own stuff, their own caches, their own memory. They're all alone and isolated.
Exactly.
Okay.
So great. So
cool.
Let's run this.
And we're not really doing any work. We're just calling a function that's not being inline, that's chilling. Okay.
That was too fast to see what I wanted to see. Let's...
Got to sleep?
Yeah, let's do spin weight. How's that?
What's the difference between spin weight and sleep?
Spin weight is basically keeping the processor active. It's a for loop.
Oh, okay. So it's the sleep the way we used to do it. We're not supposed to do it, but you wanted to keep it up.
Sleep is basically telling the kernel, take this thread out of rotation, put it aside, and when your timer fires, you can bring it back in. Oh,
cool. Okay.
So let me run this again because we missed a little bit of it.
Sorry.
No, you're fine. So we have these 4. These are each processing the same amount of work. We started them all at the same time, but we just saw that the one that was handling 0 through 20,000 just completed. No one else has completed yet. Just the one for 0 through 20,000. And in a moment, we're going to see that the one for 20,000 through 40,000 completes. There it is. And then at some point, the one for 40 through 60 will complete, and the one for 60 through 80 will complete.
Is it significant that they're completing in sequential order?
I
was kind of thinking randomizing. They're very much in line. They're queuing up. This doesn't feel very parallel.
Well, but it's not sequential like you might mean it. If I can reorder these, right? I could do them in whatever order.
Oh, okay.
It's my commas.
Yeah.
And we'll see the exact same thing happen. So the 0 through 20,000 is still going to complete before the 20,000 through 40,000, and the 40,000 they're still going to complete. And the reason,
in order, they're completing in numerical order, and I would not have expected that.
But the reason for that has nothing to actually do with the order in which I launched them or anything. It's how much work they're doing. How much work they're doing is actually not the same, because that do work function is going from the lower bound to the upper bound, and it's doing amount of work. Thread.spin weight is basically, if you give it 10,000, it's going to spin 10,000 iterations.
Oh, okay. Yeah. Okay. It's waiting longer.
Yeah. So it's basically n squared work. And the latter part has a lot more work to do than the starting part. It'd be like if I had an array, if the work here was an array.sort, right? Sorting something with 0 or 10,000 or 20,000 elements is much faster than sorting something with 60,000 or 70,000 or 80,000 elements, right? And so if I give all of the more expensive work to one partition, and I give all of the less expensive work to another partition, the one with the less work is going to finish way faster.
I see. So you, or in this case, since it didn't work very well, we'll assume me, naively partitioned the work based on what I perceived to be the work, but the reality was that this is not balanced or partitioned work. It is arbitrarily chopped up.
Exactly. It's not arbitrary. We did a very clear, like this chunk and then this chunk.
Yeah.
And if the work was even across all of the eyes, if every index had exactly the same amount of work, that might be the best possible strategy. But if there is a differing amount of work for each index, that's probably, unless it's like sort of, randomly ends up being evenly distributed.
Right.
The happenstance, you can end up in these situations where the amount of work per element is actually increasing.
Okay, but we know because of line 22 that, and the way that this is designed, that waiting 80,000 is going to take longer than waiting 10,000. But what if it's indeterminate work? What if it's Schrodinger's cat level work? I still want it to be balanced, but 9.2 is deterministic because we know, but like, I don't know how long it's going to take.
Exactly. And so that's where we end up with this struggle. On one end, we don't want to kind of just, a very simple way to address that, kind of not the best you could possibly do, but on average, sort of the best you could possibly do would be just give out one element at a time to each of the participants. Imagine you just had a bucket.
Chunk the work less, and then come back when you're done with your paper. I'll give you the next page in the test.
Bucket, and I pull out the next one and I process it. And but if I then do that naively, now I'm back in the false sharing world because the next one I grab might be So Parallel 4 and Parallel 4 in particular is trying to balance these different concerns. And it tries to partition the work up in such a way such that the threads are all operating on different parts. But when one of them runs out of work, it's able to basically help out one of the other partitions and say, I'm done with my part. You got anything for me? I'm happy to help. And it can go and like basically steal work from the other partitions to help make forward progress. Because in this example, each of these threads, when it was done, it just stopped and just sat there and twiddled its thumbs. I was like, all right, let me know when you're done. I'm going to go have a coffee, right? Instead, Parallel 4, basically the threads say, okay, I'm done. I'd like to do something. I want to contribute. Who's got something for me? And it can go off and pick up that piece of work. So that's a lot of where the complexity in the implementations come from, is doing that partitioning better. There's other complexity as well. Talking about the hard parts, I guess, but maybe that's fun.
Well, we'll make another show called TooDeep.net where people say, dude, stop. We need to... Talk to me about the electrons. Where are the photons going, Stephen?
Well, then we have to go talk to different people. That's where you lost me. That's too deep for me. The other thing here is, I'm basically, like we saw with my parallel invoke, that I'm giving this, I have 4 actions. So I'm going to end up doing, 4 tasks, right? A task per action. But if you remember when we were talking about the thread pool, I think we talked about this, how a lot of the logic that goes into the thread pool, you could write a very simple thread pool in like this much code. Right? Mm-hmm. Saw that. And for the most part, that code, if you look at the real one, the corresponding functionality is a little bit bigger, but not like orders of magnitude bigger. The vast majority of logic in the thread pool is going into things like thread management. And one of the things the thread pool tries to do is adapt to sort of the changing nature of workloads, say on a server. So you might have a burst of work and then there needs to be more threads, and then it becomes nighttime and people stop submitting requests and the work goes down. And then Australia wakes up and, lots of requests come in, and there's different times a day have different activities or different whatever. So the thread pool is all this logic to kind of constantly be monitoring and constantly experimenting. It's a really good experimenter. It likes to try things. It likes to introduce threads. And if that helped with throughput, great. It keeps it in the rotation. And then if it didn't help, it tries to remove it. And it sees like what these experiments do. That has a really interesting interaction with these types because effectively these types are queuing some number of tasks that will logically try and consume as many threads as the thread pool is willing to give. Right? And in fact, the actual implementation for Parallel 4 and Parallel for each is literally implemented like that. It doesn't queue n tasks initially, where n equals processor count. It queues one. It queues one task. And when that task runs, the very first thing that task does is queues a replica of itself, such that if another thread becomes available, that thread will pick up that replica. And then the very first thing that replica does is create a copy of itself, so that when another thread comes along, it picks up the replica. So it spreads itself, it creates tasks dynamically, spreading them out across all available threads in the system. So if you are on a server, you've got lots of requests coming in, you got a parallel for happening on each request. Each of those isn't going to create end tasks. They're going to create one task each. And then when that task runs, it'll create one more that'll just sit in the thread pool's local queue. And no one else is going to pick that up. It's just going to kind of sit there waiting. And then each parallel for is going to, that one task will end up completing all the work and the whole thing will go away. But if there was a lull and there was only one request, well, then another thread will steal that work from that other task that was created. And then that thread will run that task and it will create a clone that will go into its local queue, and another thread will steal it, and it'll very quickly replicate itself across all available threads, which is cool as long as either the work is relatively short, so it's not going to hold on to stuff for a while, or those tasks find some way to play nicely with that experimentation. Because if the thread pool injects another thread and immediately that other thread is used to pick up that replica, and that replica queues a copy, and then another thread, the thread pool experiments and injects another three, like all of those threads immediately get used. And if they stay used for a while, the thread pool has no opportunity to complete experiment and take those threads back because they're all being used. And if that loop just stays around forever, every thread that gets injected keeps getting used, and the thread pool is like, oh, this experimentation, I don't know what to do with it, right? You can't take the threads away. So there's additional logic in these parallel loops to actually have these tasks go away every once in a while. So they will I don't remember the exact number, but say, it's random. There's some randomness built in. Let's say
it's not like my brain just went to garbage collection, but it's really breathing room. It just needs a little breathing room, just a moment to catch its breath.
Exactly. So the task says, you know what? I've been running for 200 milliseconds. Let me create another clone of myself, and I'm going to go away. And then thread pool, if you still have a thread for me, please pick up that copy of myself and bring me back.
Okay.
Right? If you don't, well, then that task is just going to sit there and either be picked up eventually, or just it won't be needed and it'll go away eventually. So there's that kind of logic as well to deal with that complexity.
It's so funny how my brain goes, like, I'm talking to you, it's just like I'm scratching my eye, but I'm scratching my brain right now, you know?
I think that's a good thing.
The analogies and like when I come up with analogies to try to explain this, in the audience is like, oh, that was a decent analogy. It's also to like, it came in my ear, it got processed, and now I have to put it out my mouth to make sure I understood what you just said. And my brain just went to the movie Waiting to Exhale with Whitney Houston. But I was just thinking about like, wow, okay, so the computer really needs to just go, yeah, are we doing this right? Okay, we are. Let's keep going. And that's what I went to when you explained that. That's so cool.
Yeah, it's like, if I take our kids to a playground or something and they say, can we go off? Yeah, sure, but just check in with us every once in a while.
Yeah, just come in, man. I'm still here. Everything's okay.
Exactly.
Yeah, and my kid's 18, and I'm just like texting, "Are you live? Okay, I'm alive. Okay, cool. Thanks. Continue running in the streets.
Exactly. Do your thing." Or they kind of like, "Can we keep playing? Actually, it's time to go now." Yeah. So there's a lot of complexity built into these things, but we try and hide most of that complexity behind the APIs, and where it's relevant, we try and even expose more primitive level constructs to allow you to kind of reuse that logic in situations where you might want to use it separately, or allow you to tweak it a little bit. So let's look at another example here. So
and something else I don't want to send you in the wrong direction because I know you have a plan here, but something to be maybe think in the remaining kind of half an hour. I did want to ask, you're going like this and you're waving your hands and we have some text on the screen, and maybe most of the people can visualize this, but visualization of work, multiple threads, debugging multiple threads. There's the got here debugging, which is the console.writeLine. Got here. And like, oh, the order of these is different. So that must be parallelism that's causing that. Are there any tools or visualizers within Visual Studio or ways to think about threading call stacks across multiple threads? And is that something you could weave into this explanation so that people might more viscerally understand what's going on?
Absolutely. Let me just put a pin in that for a moment, finish my thought, and then we'll come back to that.
Yes, sir.
Because I just wanted to highlight, there's a little known type that I actually love in .NET that is implicitly used by plink and Parallel4 and for each, but it's also exposed. And it's this type called partitioner, which basically handles that partitioning complexity and exposes in a way where you can just consume it. So actually,
I have never in my life heard of this type.
Right? No one has.
I love it. You've just like gone into it's like you live in a house and you discovered a room that we didn't know behind a wall. That's crazy. Okay. Yeah. Partitioner.
So here's our Parallel4 each, for example. And when we're creating, we're saying for each item in source, like spin up a task. So this isn't particularly efficient. For a couple items, it'd be fine. For a lot, it would be a lot of overhead. So instead of this, maybe I want to do something like this. Maybe I want to say, I'm going to grab an enumerator. Let's do that. And then I'm going to create a bunch of tasks. So we'll say from I in enumerable.range from, I don't know, environment to processor count. Let's see what it did. That's actually pretty good.
Yeah,
nice.
Nice.
It's the other thing with I know we're not an advertisement for Copilot, but one of the things that's important for people who are using Copilot to do is to make sure you look at the code that it generates, because it's often quite good, but sometimes it's not exactly right.
It can be subtly wrong, especially doing this kind of work. But like we both exactly did the same thing. We're saying, yeah, okay.
Yeah, exactly. Is this what I was going to write? Yeah, close enough. So what are we doing? Well, we're basically saying we're spinning up n tasks, and we have one shared enumerator, so one source of truth for all the remaining data to be processed. And we enter a loop where we take a lock because we are accessing this shared thing, and we see if there's anything else. If there's not, we're done. We exit. If there is, we grab it, we exit the lock, and we execute the work item.
Yeah, and it's very important to note you would not want line 20 on the inside of that last bracket, because then you'd be in trouble.
Yeah, if you did that, you have eliminated all benefits of parallelism.
Yeah.
And worse, you've actually taken arbitrary user code, consumer code that has no idea that you're using a lock, and you've invoked it while holding the lock, which can create very, one of the necessary components of a deadlock, for example, is that you have mutual exclusion. And if you have mutual exclusion, in this case, the lock, and you're not telling anyone about it, you kind of increase the chances that there's a possibility for deadlock. Because you're doing something while holding a resource, and if that tried to do something that required another resource that was held, you can't make forward progress. So this is fine. This is functional. But very similar to the issues that we faced with the Parallel4, where we're having to think about the ranges and we were having to think about false sharing, we run into similar but different issues here, which is I'm now locking every single time I access this enumerator. And if pushing this enumerator forward was costly, this could end up kind of taking a substantial portion of my time. Or if it wasn't costly, but my action was cheap, I'm spending the majority of my time just synchronizing on this enumerable. And I don't want to do that either. So what I kind of like to do is employ better partitioning. Maybe I take the lock, and then rather than grabbing one item, I grab 10 items. I release the lock, and then I can process those 10 items without having to take the lock again. So I've kind of amortized the cost of taking the lock across all of the elements that I grab out of the enumerable. But now we run into a similar partitioning problem where what if I grab 10 elements that are the most expensive 10 elements? The first thread grabs 10, the next, or maybe I think we're talking about 80,000. So let's just say I grab 20,000, the next one grabs 20,000, 20,000, 20,000. And yeah, I've reduced the cost of the lock, but I've distributed all of the expensive work to one of these. So what you kind of want to do without any additional a priori knowledge is start small. Yeah, let's grab one. Let's grab another. Okay, now I've grabbed one several times and I'm still running. So this time, let me grab two. And now I'll grab two again. I'll grab two. Oh, okay, that worked. Maybe this time I'll grab four. And you can kind of ramp up that way to kind of more evenly distribute the work and make sure that one thread isn't kind of taking all of it. And then you max out at some point, maybe 16 or 32. Say beyond that, it's not worth amortizing the cost of the lock. anymore, and I don't want to risk taking all of the expensive work and bringing it in.
My wife and I do Christmas cards. We're old and silly, and we do Christmas cards. And I do the mail merge, and I go in Excel, and we have like the Christmas list, and then I print out on Avery label sheets like all the stuff. So then we will sit like around November timeframe, and we've got the Shutterfly cards that came. We've got the envelopes. We got the licking of the envelope. We've got the return label, and which come on like rolls. And then you've got the stamp, and then you've got good cores, which are the parents, and then you've got the efficiency cores, which are the children. And then like who's really good at this? Like who's gonna do the licking of the thing? Do we get a and it's complicated distributed work amongst multiple cores that have some ability. So let's just do 2 or 3 and see how do we feel about that. And we have 150 mailers to do, and it's just this constant rebalancing of work and efficiency. Like, oh, all the stamps are done, but nothing has been enveloped.
Exactly.
That's exactly what's going on. All right, this is great. So I get it.
I'm going to rename this to "Licking of the Envelopes of Tea."
Oh yeah. Okay. So I get how this is being partitioned now and why it can be good or bad.
And so but I don't want to have to code. That was a very complicated algorithm I just lined.
Keeping 100%.
Time on that. So there's this built-in type called partitioner, which has a bunch of overloads, one of which just takes an enumerable. And this is going to give back a partitioner of T that has various methods on it, like get partitions. So let me just call this, and I'll say I want back processor count partitions. And this is going to give me back partitions, which if we look at the actual type, not sure why it used global.
That was weird.
Very weird. These partitions are a list of these enumerator of T's. So now I'm just going to say, instead of doing this here, just delete this, and I'll say for each partition in that.
Okay.
And I'm just going to simplify this to while partitioner.moveNext, partition.current, and it's also a disposable thing, so I should really say partition and do that. So now the partitioner
got very clean.
Yeah, exactly. It's created these enumerators, one for each partition. And internally, it's doing all of that complicated logic to figure out when I call move next on the partition, what's going to happen. It might have a buffer of multiple items. So when I call it, it might grab several. It might start grabbing 1 and then grab 2 and then 4. It handles all of that for me. Is
the magic of the handling of that because it's an iDisposable object? So it's kind of the scope of that using, there's some like implied work at the beginning and end of that?
It's less the disposal here is just to make sure that any resources that it created it can.
Okay, but there's no magic in that because sometimes people will override the iDisposable pattern and like hide the work around the scope.
It's the only purpose for the purpose for this is really when I call get partitions, it's basically calling get enumerator on the underlying source, and some iEnumerator is an iDisposable. Okay. And some enumerators might have disposable resources.
I see.
When I finish not just one partition, but all of the partitions, it needs to clean up that underlying enumerator.
Okay. I guess I'm trying to understand where the magic is. Is the magic's in move next then?
No. And so if we just care about the magic, I can do this. And then the worst case is I'm not disposing that.
You don't clean up. Okay.
Yeah. So that's the basic idea. And once I've kind of abstracted that away, now I can create different partitioners for different purposes, or I can control things. So for example, if I really did want the one at a time logic, but I didn't want to have to write the lock, I could come in here and say options, no buffering. And so now it's going to just cut out all that complicated stuff it was doing to try and better distribute stuff. And it's going to say, okay, you're just going to get one at a time, right? And so you can kind of control it behind this abstraction. You code to the abstraction, and then different implementations can come in and plug things in. And you can see on partitioner, it's able to partition various things. So it's not just partitioning enumerables, but for example, it could partition from a from to a to. And so this is basically what Parallel 4 is using, where it's saying, all right, I'm going to partition up this space from a 4 to a 2. And this partitioning will try and it'll give each worker basically it'll allocate to it effectively, n divided by number of workers work. So it's largely contiguous chunks. You get nice locality of reference. You avoid false sharing issues. But in such a way where when one of those workers finishes and it goes to say, hey, I'd like the next piece of work, please, they'll say, I ran out of my local chunk. Let me go coordinate with those other folks over there and see if I can grab some from them. So it handles that logic under the covers so that the developer doesn't have to. That said, if what you really wanted, was ranges, it can support that as well. In fact, that exact overload I was looking at may have been the one for ranges. I was just noticing the return type. It's giving out tuples. There's another one that will do sort of the more elaborate scheme. Okay, so that was my cell for partitioner, just because I really like the type. I think it's fun. And if you look at parallel for each, in case you want to use your own partitioner or write your own, you can use the logic associated with scheduling and whatnot from parallel for each, but you can not only pass in an enumerable, you can also pass in a partitioner. And so you can basically say, okay, I want to use your logic for processing work in parallel, but here's how I want you to divvy it up.
Because I know more about how to lick envelopes, and I know
that my work is super evenly distributed and there's nothing else happening on the system. So I'm going to give you a partitioner that has zero overhead and does just a linear division into equal size chunks. It gives you that control.
That's cool. I've never heard of that type. That's crazy. That's not often that I discover an entire room in my house I didn't know existed. That's very cool.
And P-Link has similar support for, if I have a partitioner, there's an as parallel.
Yeah.
All right. So you were asking about
visualizing. Yeah. It's like, there's a lot going on there. And I feel like when we learn this stuff, when I see folks on YouTube talking about parallelism, we end up at the console and we see a bunch of out of order console.write lines. And I was just curious if there were any visual tools for better understanding parallelism. So,
let's take a few examples. Let's take one where the work is relatively uniform. So
we get about 15 minutes before we all have to go back to work.
Perfect. So I'm just going to have a method A that calls B, and I'm going to make sure this can't be inlined, just so we can see it. Because when methods get inlined, their code is copied into the caller, and then they evaporate, and so you wouldn't see them on a stat trace if they're inlined. But I want to see them. So we're going to do this for a few things. We'll do A. We'll do B calling C and C, and we'll do C, and we'll have C just do a thread.sleep for, a bunch of time. Well, let's make this really big, just so we can break in and see what's happening. And then I'll say parallel.for 0 to 10. And we'll invoke A. Right. So pretty simple scheme. Now, the way I've set this up, basically all threads they should all end up in the same place. They should all end up kind of stuck in C. So I'm F5ing this to run it with the debugger attached.
And folks could think about that in any way. Like, A could be the front end and it calls the middleware, and middleware calls a database, and the database is slow. And then no amount of parallelism is going to make that go faster.
Exactly. So I'm going to break into this in the debugger. Mm-hmm. And I could look, I don't think I can make this. Can I zoom here? No, I can't zoom. I don't have Zoom it running, but hopefully it's the core part is, let me start zooming actually.
You could also use the mic. Yeah, there you go. Thank you for doing that. I think people on their phones appreciate that work.
I learned from you. I'm supposed to.
I know. I appreciate you. All right, there you go.
There's you see it with one thread. It was in, was in main, and then it called through a whole bunch of stuff. We're in main here, and then we called through a whole bunch of stuff going up through parallel, and then we enter into tasks. We're back into the parallel worker, and then we're up in our call stack here, A calling B calling C. And this extra gook, this dollar underscore, all that extra ceremony, that's just because I used basically local methods, top level local methods. And so the compiler is generating a mangled name, but you can still see the original name there. And then eventually we end up in sleep. Now I can, let me put this down here. I could go from thread to thread and look at each of the different threads. Or I can bring up the parallel stacks window up here. So now we can see in one view kind of all of the threads in my application. And you can see that it's grouping them based on call stacks. It's basically creating these cactus stacks where it starts at the bottom, and when all threads have the same set of frames, they're grouped together. And then when they diverge, you see that. So there were 11 threads that started here in worker thread start. Mm-hmm. And then 2 of them went off here to call semaphore.wait. And 9 of them veered off to call this ABC.
That's so cool.
So you can see this, very easily, and I can zoom in on particular things. Let's say I just wanted to see everything that had a frame in A. So I could actually, I didn't mean to double click. I could say, where's the button? It is
switch to frame.
Yeah, there we go. Toggle method.
Yeah, there you go.
So now I'm seeing that there are 10 threads, which is what we expected because we had our parallel for each was 0 to 10. Mm-hmm. We can see that there are 10 frames in A, and now we see how are they coming in. So we've kind of refocused, and we've got all 10 of these are going up into B and C.
And when you hovered on that, by the way, sorry, you hovered on that, I can see the instruction pointer is on a specific thread. So it's really trying to let you know the relationship between what's happening and where you're thinking it's happening in the text editor.
Exactly. So this is still the current thread. This is what I just saw in the thread stack. Right. But I could switch to another one and jump into there, and the thread stack would reflect.
Oh wow. Okay, sorry.
Like that one. Now if I go back to, you'll see the current one has now moved. Now it's the one I switched the current thread. This kind of tool is super useful. There's also a tasks view for this. So rather than focusing on all threads, I can focus just on the ones that are running tasks. And then I can just focus in on kind of eliminate the extra ceremony that didn't have anything to do with tasks or user code, and see just the ones that are relevant to that view. In this case, if we go back to threads, we can see that because of how, let me switch back to threads view. Did it work? Sorry, not method, this view. So there were 9 threads that are running as part of a queued task. But because of how Parallel works, this is actually another great thing to call out. Parallel, we were basically launching 10 tasks and then blocking. But we already have a thread. Like we have a thread right there. We don't need 10 other threads to do the work. We could instead have 9 other threads do the work and then use the current thread to run some of it. And so that's reflected here. We can see that 9 of them are, in fact, in thread pool dispatch. But one of them is actually being invoked from main because main called parallel 4, which said task, run synchronously. Mm-hmm. And then that ended up calling into our code on that thread. So it's trying to be smart about utilization of resources. And we can see that when we view it from this threads view. When we dive into the tasks view, we don't see that 10th one that wasn't actually a task, right? It was
yeah. And I also like the word. It puts the word logical there, like it's distinguishing between how you think about how you structured it versus how it ended up being scheduled and how the processor thinks about it, and the physical versus the logical.
Relevant for async programming, because if I change this, if I actually said async task for these. And I changed all of these to async task, and then I changed this to await task.delay. Instead of a thread.sleep, let me do task.delay. And I also need to await. Mm-hmm. I can't, let me do.
Can't await that.
Wait, parallel or async. Async. So, and this also takes a cancellation token. We're going to ignore that. There we go. So now I'm going to run this again. We're going to see the same, we're waiting for stuff to happen. And I again break in. I'm not sure why it's trying to decompile that, but it doesn't matter. We again see our logical stacks because this isn't a real stack. Like these were async methods. They're not on any threads.
Synthetic.
It's synthetic, but it's stitching together main called A, called B, called C, called task.delay, and there were 10 of them.
Yeah.
And they're all just on the heap somewhere because all the state has been persisted. But the thread, if I look at the actual threads view, there's no thread ABC. Right?
Yeah,
I've got a bunch of threads that are all just, these are all the ones here. These are all just blocked in the thread pool waiting for work. They have nothing to do. So they're just sitting there idle. Meanwhile, this thread, the main thread, is waiting on basically, getting in the weeds, but we have a synthetic async main method that the compiler generated for me because I was awaiting.
Right.
But the caller of that async main needs to block, because if it didn't, then the process's main thread exits and the process goes away. So what we're seeing here is the compiler generated main blocking.
Because you're using top level.
Yeah,
Yeah,
exactly.
This is such a great view. Like, again, like this is the different, like there are people out there in the world who are like anti-debugger. And they're like, nah, I do everything with console.writeline. Like this is so good.
And this is a simple case. The cases that are mind-blowing are the ones where someone gives you a dump and it's like, my service was running for 6 hours. I have 32,000 threads. Tell me what's wrong. Here's the dump, right? And if you have to click through 32,000 threads and do your own manual, whereas this is just like, 31,000 of them are stuck on this call stack. Okay, that's where I'm going to look. Right?
Yeah, that's so cool. So you can bring that dump in and it gets bucketed, and this is where an IDE really shines, in my opinion. My alarm has gone off and I have to go talk to Scott Hunter. So we have about 2 minutes to wrap up.
Let's call it.
You want to call it?
We've taken a pretty windy tour here, but I think we've called out a bunch of the kind of intricacies that show up as part of Parallel 4 and for each and Invoke, and hopefully people have a better sense of why they're 1,000 lines out of the 2 lines that I wrote.
Hanging out with you takes my .NET. It's like playing Tetris. There's my .NET knowledge and what I think I know, but it's fragmented and it's kind of, it's got these gaps. And then this like L-shaped piece comes down and rotates and snaps in. And then it kind of goes, you know what I mean? So like, I thought I knew it and like, oh, now I know it better. Thank you for that L-shaped piece that just like completed the row and made me feel much more powerful. I hope that folks appreciate this. If you made it an hour and 15 minutes into this video, drop us a comment. Tell us what you want to hear from. And we're going to bring in probably in the next episode or two, some new friends to talk about more deep .NET topics. Thank you, Stephen. That was a joy.